Thank you, ladies and gentlemen. Thank you for my able assistant there and the wonders of rebooting Linux. We're a compiler company and operating systems these days, but we're best known as a compiler company. And we're doing a lot of work on RISC V, both GCC and LLVM. But our particular speciality is deeply embedded systems, and for deeply embedded systems you want your code to be very compact, and so my focus is on how do we make the compilers generate very compact code, -OS, and if you're LLVM, -OZ as well. You can only improve something if you can measure it, and this is about measuring the size of compiled code for RISC V. And this is to help compiler designers. So this talk is about seeing inside the compilers, looking at what's working, what's not, investigating and understanding it. One thing I want to be clear is it's not this. I'm not trying to tell you which is the best processor or the best compiler. And we've looked at three architectures. We've looked at the Designware ARC HS, the ARM Cortex-M4 with the Thumb2 instructions, and the RISC V RV32 IMC. Those are all 32-bit architectures. They've all got 16-bit short instructions, and in all cases we've been looking at them without hardware floating point. The Designware ARC HS is a bit out of place there. We really ought to have looked at their EM architecture, which is their embedded architecture. The reason it's HS is because the customer we're doing this for is using HS at the moment and wanted a comparison with that. So they're all similar architectures, and what we're trying to do is to find out which of what they do well and what they do badly each as a compiler. So what to measure? Okay, so what we got? How are we going to measure this? Well, we're going to use Beebs. How many people here have heard of Beebs? Okay, it came out of some research into energy efficient compilation that we did with Bristol University 6 or 7 years ago, and it's the Bristol Embicosm Embedded Benchmark Suite. It's a free and open source test suite. It aims to have a mixture of types of programs, so some that do a lot of branching, some that do a lot of memory access, some that do a lot of integer operations, and some that do a lot of floating point. It's designed. So many benchmark suites assume they're going to print out the answers, which if you're deeply embedded is a real problem because you generally don't have printf. So we try to have minimal I/O here, and the results are captured without actually printing anything out. There's a paper on the research behind this on arXiv, the link's on the screen. It was originally just 10 programs. Those are shown in the table on the left, and they're color-coded according to how much they work, their code reflects different types of operations. Beebs version 2 now has 79 benchmarks, and I've got a task to do, which is to actually reproduce that table for all 79 benchmarks to show that we've still got a good mix of programs. So what are we going to measure? Well, let's look at it as a picture. Broadly, in an embedded system, like any program, you've got a mixture of code and read-only data. Those always go into ROM or flash. Some initialized data, which is writable, so you put it in RAM, and uninitialized data, BSS, which also goes into RAM. And any RAM you've got left over, you'll use for your stack and your heap. So you might think we should look at how much size code and read-only data state, because that's going to tell me how big my ROM's got to be. There's a bit of a question over that, because initialized data has to be initialized from somewhere, and you usually put that into ROM as well. But for the purposes of this talk, I'm just going to focus on the size of code and read-only data, because that's the key thing, and it's also because that's the figure that the standard Linux size program gives you. So the absolute statistics we have for each of those 79 programs, we're going to capture the size of the code and the read-only data, and we're going to record a total amount of data. That's going to be dominated by the large programs, because one large program will have as much as 10 small ones. And we'll also record the size of the largest program and the size of the smallest program. But we'll also look at some relative statistics. And we're looking at 3 processors. I've taken RISC V as the baseline because I'm talking in the RISC V dev room. It could have been any one of them. It doesn't matter. It's just an arbitrary choice. Okay, and we'll look at each program in turn relative in code size to RISC V. Is it bigger? Is it smaller? And we'll take an arithmetic average of those. And because all these sizes should be close to 100%, then we're not going to get any distortion. We'll use the arithmetic average. That should be fine. We don't need to worry about geometric or harmonic means instead. And we'll also look at the smallest relative size. So in other words, which program on this processor is so much better than RISC V or so much worse than RISC V. And those are really interesting because they're ones where the compilers are clearly doing something different. So those are the statistics we're going to record. So let's just run some statistics. And I don't expect you to be able to read the individual programs off here, but let's just run the programs, compile them, put them through size and measure them. And there we've got in yellow the ARC processor, in red the ARM processor, and in blue the RISC V processor. And you can see some programs are big and some programs are small. What you might notice is that the ARM results, the little red results, never get below a certain point. There's quite a lot of small programs where there's a reasonable size spike for ARM. And in fact, if we look at the detailed statistics, we see that. We can look at the total, but the minimum size you get from an ARM program is 4K, whereas ARC and RISC V both under 1K. If we look at the maximum code size, incidentally, the biggest program for RISC V is notably a lot bigger than the biggest 5 for ARM or ARC. And if we put the relative percentages in, on average, ARM's coming out at being 222% the size of RISC V, and that is because any small program is coming out 4 times as big, so it's skewing that average there. For ARC, actually on average is slightly better than RISC V on this case. And the smallest programs, ARC has some programs that can do twice as well as RISC V, ARM has some similarly twice as well, and both ARM and ARC have some really pathologically different cases where they're far bigger than RISC V. So why does ARM do so badly with small programs? Well, let's look at the smallest program called NS, and look at the symbols in there. And if we run NM on it, we can see there are 61 symbols defined in the ARC program, 130 symbols defined in the ARM program, and just 43 symbols in the RISC V program. And in particular, look, the last one there's 2 write functions in. Why is a program that does no I/O showing write inside its list of symbols? And the answer is the ARM startup code is pulling in a lot of standard C library code. That C runtime startup CRT0.0 is a problem. So it's distorting the results, and it's not allowing us to see what's really going on in the compiled code, because it's just a big chunk of code bolted onto every ARM program. So let's put a dummy CRT0. We're only looking at code size. We don't have to run these programs. So let's just put a dummy in there. And when we put the dummy program in, we get a different graph. And you can see most of the ARM spikes of small programs have gone away. Not all of them. We'll come back to that later. But most of them have gone away. And when we look at the number of symbols, now we see we've mostly got the small number of symbols. We've got rid of all the symbols, not just from the startup, but from the C library code it was pulling in as well. So we're getting a better comparison. And we can see here, well, actually things change around. Now ARM is looking relatively, is much better. It's not 200% bigger on average, it's 111% on average. ARC, actually, which was better, is now looking a little worse. Okay, and the smallest programs are now tiny because basically they're tiny little programs, and the biggest programs, not surprisingly, unaffected because the size of startup code was trivial. And so some of the larger programs do use the C library. All the bigger ones, they have to use them for some things, even if they're not doing I/O. And what we observe is that quite often these programs are often larger for ARC and ARM. Not all the case, but ARM and ARC seem to have bigger, the big programs are noticeably bigger. So let's see whether the standard C library is causing a problem. And so we'll, just as we put in a dummy CRT0, we'll put in a dummy standard C library. It just has dummy programs for any C library function you're going to use. No content. And what we see here is now suddenly ARM looks very good. And in particular, you may not notice the very worst ARM program relevant to RISC V is now only 18% bigger. None of those several 100% bigger. So the pathological cases have gone away for ARM, suggesting there is some pathological code in the C library that's linked into one or two programs. The problem hasn't gone away for ARC. Its worst program is 7 times as big as its equivalent RISC V program. And we see now ARM is starting to look really quite good. Okay, it's 17% better than RISC V. Okay, so what's actually useful is to let's have a look at the total size of code, because we'll look at it when it had the standard C library and then we'll take the C library out. And what we can see here is that when you take the C library out for ARC or RISC V, the total code size goes down about 6%. But for ARM, it goes down 24%. And that's telling me that if you look, the ARM standard C library seems to be very, very big compared to others. Okay? It may be, we're still trying to find out, it may be that it's actually compiled focused on size. There's only one C library, and if it's been optimized and unrolled all its loops, of course it's going to be big. You really need to have a multi-lib variant for compact code as well. We also know, because we've seen it there, that the library is not done at one function per file in the library. So if you pull in one function, you're going to pull in a whole load of other code. So you can't do the garbage collection of sections on it. So, but we're getting rid of more confounding effects. So any effects of I'm distorting my figures because I'm just not looking at the compiled code, I've got this big wodge of C code stuck on the end, we've got rid of that. But some notable variations. There are some programs, Cubic and Frac, where RISC V, ARM and ARC both do well compared to RISC V. ARM in particular, less so for ARC. And the clue as to what's going on is when we look at these two programs, matmult float and matmult int, which are the same program, matrix multiplication. One is done with floating point numbers and one is done with integers. And we see for the floating point one, ARM does really much better than RISC V, where the integer one, it's almost the same. And that gives a bit of a clue that ARM seems to do a very good job with floating point. ARC's a bit more variable. It's not quite sure what the message is on ARC. Now remember, these are all chips without a hardware floating point unit. So this is about floating point emulation. So that's done in libgcc, because this is the GCC compiler. And let's see whether it's actually that ARM has got a super compact floating point emulation. And we'll do exactly the same thing is we'll put in a dummy libgcc. And so now we run the same things again, and things are starting to get much closer actually. We're seeing fewer extremes. And let's put it again. And if we look at the table of data, okay, what we see is that actually now ARM is not so good compared to RISC V, and indeed ARC is coming more into norm. And we notice now the pathological cases for ARC have gone away, suggesting that ARC's pathology lives in some of its floating point emulation routines. Okay? So now we've got rid of distortions from a block of startup code, distortions from pre-compiled C library, and distortions from the emulation library. We're looking much more just at the code we actually compiled for this test. And we can see the impact of the floating point library if we look at the absolute total. So if we look at the total code size, and we can see that for ARC and ARM, when you take the floating point emulation away, you get rid of, for ARC and RISC V, you get rid of a third of the code. Okay? And when you do it for ARM, you only get rid of a fifth of the code. So ARM's clearly got a much more compact floating point emulation. Okay? Now I've actually taken away libgcc, and of course libgcc does more than just floating point emulation. So we do just need to check it is the floating point emulation, not some other emulation in there that we're worrying about. The last thing is to say, well, we looked at libc, let's look at libm, the math library, because we all really ought to see, is that having an effect? Does one architecture have a particularly good maths library? And actually, when we look at this, the figures don't change much from what we saw in the previous round, and we can see that when we look at how much is saved in the absolute code size. The math library basically accounts for 6% of the total code size. It's the same for all architectures. Almost certainly everyone's using the same CMath library, just compiling it it's going to be proportional, it's all going to come at 6%. But it's still a block of pre-compiled code, and if we're looking at the effect of the compiler, we ought to take it out. So if we look at the overall summary, we have the figures at the top for the baseline where we just compiled the programs and look at it. But as we go through the lines, we've stripped out the distortion of a block of pre-compiled startup code, the distortion of C libraries, which are of different quality and are pre-compiled, the distortion of the emulation library and how its emulation is done, and the distortion of the pre-compiled math library. And if you take all of those out, the bottom line there, really all you're looking at is the size of the code you actually compiled. And for the purpose of the compiler writer, that's the one that's going to give you insight. Now I've just put the averages there. If RISC V is 100%, ARM is coming in about 8% better, and ARC is coming out about 14% better. But I emphasize this is not a beauty contest because there's a lot of variation. Okay, if we go back up to the previous slide, no, the previous one slide, we'll see there are some programs where ARM is worse and some program where it's a lot better, and the same for ARC. There's some where it's really very much worse and some where it's much better. So the takeaway is useful results for compiler writers you need to only consider the code you compiled. Okay, libraries and startup code confound the results. So remove your startup code, remove your C library code, remove your emulation library code, and remove your math library code. That's easy actually in this case because I'm only looking at code size. You have to actually try and remove the same factors when you're doing execution speed, and that's a talk for next year because actually it still has to work. But code size is what we were looking at. And what comes out of that then is some useful graphs. You can compare ARC against RISC V, relative size, and order them. And the interesting ones are the ones at each end. Okay, the functions that are cubic, for example, where ARC is nearly twice as good as RISC V. Or I can't remember. I can't read it. The one at the other end where ARC is almost twice as bad as RISC V. And those are ones we're going to delve into, because why is the compiler, which is still GCC, so different for those programs? Because there should be something at one end that ARC's doing really well that RISC V isn't, and the other that RISC V is doing well and ARC isn't. So this is good for both the ARC compiler team and the RISC V compiler team. And we can do the same for ARM. Variation is less there, but I'd still like to know why are there some programs where RISC V is 18% better. I'd certainly want to know why is it that cubic again is 50% better. And of course we can compare ARC against ARM, and that gives us insight as well. So we've got a three-way comparison here. And what did we learn about GCC? Well, first of all, and this ties in with Krista's email this morning, some new instructions would help. Now, the work, we've only actually been taking these results and actually trying to apply them to compiler since the 1st of January. My colleague Jörn Renneker's been doing that work, and I actually wrote this slide at 9 o'clock this morning to get the very latest data from him. But actually, if you had an instruction to add 14-bit constants, you'd take more than 1% off the code size of those benchmarks across the board. If you had a 8-bit instruction to load a 32-bit constant, you'd take another 1% off. And then we can apply compiler techniques, and that's what we can actually do today. The first ones will feed into future discussions about new instruction set extensions. One is millicode, which is where you find common code sequences that you keep on using, and you pre-package them. So of course those take up some space, but then everywhere you would have generated a lot of instructions, you just generate a quick call and return. And that, just the simplest millicode, we think will save us 1/3%. And that in compiler terms across the board is actually a decent win for something fairly straightforward. Putting common sub-expression elimination into the linker actually is quite a useful win. We still haven't got a good estimate. None of these other ones I've got good enough estimates for. But an increasing theme that comes out with modern architecture is you need to use the linker to do optimizations. That's not link time optimization, which is the linker feeding stuff to do global optimization in the compiler. This is actual optimizations in the linker. It's taking relaxation to great extremes. Okay, so we think that will give us a good win as well. There's more advanced millicode. Jörn's done some initial experiments suggesting that if you could have millicode function that did a scaled index load, that would actually be a win. There are, in various places, dead register loads, where you load a register, copy it to somewhere else, and then use it. Why didn't you load it into the second register in the first place? That can be done with a peak pole optimization, and that seems to be surprisingly common. We need to look at the register allocation to see quite why it's doing that. But then, if we can't fix it there, we can do a peak pole. And we can also roll up some loops. There are still places where in compiled code, in compact code, the loops are still being unrolled. And there are circumstances where that's a win even for code size, but there are very few of them. So this is a talk about measurement, not really about the compiler optimization, but even in 1 month, we've found a whole load of stuff that between them will give us a few more % off the compiled code size. So what do we need to do? We need to do more measurements. We need to repeat this for LLVM. Okay, so it's all packaged up. It'll be easy to do for LLVM. I hope to do that this week, not least because I've got a whole customer breathing down my neck for the data. I want to give ARC a fairer crack. It wasn't fair to compare HS, which is a high-performance Linux class processor. I should look at their EM processor. As I say, driven by customers, that one, but I think, you know, ARC did very well, given it wasn't in the same class. I'd like to separate out code and read-only data. Okay, there are optimizations that push stuff into data to drive the code, and you do need to actually break those out. And I'd actually like to look at initialized writable data, because that often goes into ROM as well. And we've only spent 4 weeks looking at the compiler analysis. Okay, and I think over the next coming months there's going to be a very fruitful set of optimizations that come out from looking at those extremes on the two graphs to find out why is ARM twice as good, why is ARC twice as good, why are we actually good here, what are we doing well. Okay, and that's actually beneficial not just to RISC V, but it's generally beneficial to ARM, to ARC, and to the wider GCC community. Okay, so the resources for this talk: Beebs is freely available. It's free and open source software. It's available on beebs.eu. We modified it a bit for this talk to make it easier just to drive through the stuff. There's a bit more information. That will eventually go into a new release of Beebs, but I've put you there the GitHub link to the actual branch we use. And this is all written up as an application note, which is in review at the moment and should appear sometime next week. And that's my talk. Thank you. Questions? Yes?
I think one of the differences between ARM and RISC V you didn't mention is that on ARM you can push a set of registers using just one instruction, and if I remember correctly on RISC V, you need to push and pop every register with a separate instruction. Did you actually have a look at that?
So this is the question that ARM has a multi-instruction push.
Right.
That keeps on coming up. The initial analysis suggests that it's not quite as big a thing as you might think, not least because modern compilers are quite good about optimizing away prologues. They're not rigorously stuck at the start of the function. But that's also a big driver behind the early millicode stuff, because millicode can actually give you a push-pop multiple register.
Right now, the only millicode we have in the compiler is for save and restore sequences. And it frequently ends up being bigger to put the millicode in than to just inline all the save.
So a good global link time optimization phase should actually be able to allow you to decide whether or not to put millicode in. But that's probably indicative of the fact that millicode doesn't actually win, that it's not quite as big a problem as you thought. Next one.
There are 2 comments here. One is that the analysis that you did initially, you could avoid if you took benchmarks like TIBE, because benchmarks like TIBE, they just create object files instead of the complete executables. So you can avoid LibMan and libc other dependencies. And the second comment that I have is that you should probably take a look at nanonips. Nanonips has some of the features that you mentioned here, for instance, 48-bit instructions default that do the constants and such, so it is better density and you could get something to that.
Right, so I'm happy to look at any other processors. The reason we've done these three is because I was paid to do them. Okay, so it's, anyone who wants another processor, my pockets are open. But the first part of your question, which using object code. We can use object code. What we want to do, we didn't do it on this one, is one of the two biggest improvements in compiler optimization in the last 20 years has been link time optimization. And I know I could link time optimize but not put the library in. I'd need to do object code that I'd link time optimize. So it is a possibility. It's a different approach. But that's why we didn't trivially at this case just say let's look at all the object files. It doesn't always give you the same, but it's an alternative approach. It's not right or wrong, I don't think. Okay. All right, I'm going to look this way because I've been taking questions there. Yes, there's one back there.
So you assembled a nice collection of computational kernels for your benchmark, but I'm curious how well you can use computational kernels to stand in for firmware code, because firmware code is not computational kernels.
You can't, and I am the first to say that if you're benchmarking, you should actually, the best benchmark code is your application. And, we're looking at code size here. When it comes to performance, there are all sorts of things. For example, actually where you position your code in Flash makes a big difference to energy efficiency, for example. So this is only one aspect of what you do. There's no reason why this approach can't be used with any code you use. This is about an approach. I've used Beebs. It works for us. It was appropriate in this case. But there are you can use any computational kernel you want to and apply the same thinking to it, compare it. What we're trying to find out is what does the compiler do well and what does the compiler do badly. So I think, yeah, you do it with anything you want to, and whatever's most relevant to your use case. Questions? More questions? Yes.
Do you know which standard library you use for the ARM compiler? Because there are two distributions of the official GCC. There's NuLib Nano. And NuLib Nano is substantially smaller than the full standard library.
Yes, that's what. So the question is, did we use NuLib or NuLib Nano with ARM? And I cannot, for the life of me, remember. I have a suspicion it was NuLib Nano because of the looking at small code. But I would have to go away and take that one. Even if it was NuLib Nano, I would still want to take it out because I know NuLib Nano is a lot smaller, and so there will be less distortion. But you should still get rid of precompiled libraries anyway. No, good question.
I think we're out of time.
Okay, thank you very much indeed.